Hello everyone! So in this section, we're going to talk about linear independence and we will discuss relationship of linear dependence and span. So last section, we discussed that if you have homogeneous equation, which is given in this way, then the non-trivial solution exists when there is a free variable. But in this section, so if you write this matrix equation into vector equation, then we get an equation that looks like in this way, where A sub i's are columns of A. So we're going to answer the same question using the vector equation. So suppose that you have the set of vectors in Rn, then we call that the set of vector is linearly independent if the given homogeneous system of equation has only one trivial solution. So here, if the equation star has a non-trivial solution, then this means that we can find non-zero solutions for xi's, or we can find numbers C1 through Cp in R such that these C sub something solves the given equation above. So in this case, we call the given vectors are linearly dependent. So here, this flipped E is a mathematical symbol that has a meaning of there exist. So this exercise asks us to determine whether the given vectors v1 and v2 and v3s are linearly independent, which means we have to check whether the following vector equation have non-trivial solutions. So how do we begin with this problem? When it comes to find the solution set, it is easier to think, are we fing an augmented matrix? So here, the augmented matrix of the given system of equations is given by 1, 2, 4, 0, negative 3, 5, and 2, negative 5, 23, 0, 0, 0, and it is row equivalent to 1, 0, 2, 0. So I basically multiply by 2 and 4 for the first column and subtract those from second and third row. Then that gives you 0, negative 3, negative 9, and 0, 0, 5, 15, and 0. And it is equivalent to 1, 0, 2, 0, 0, 1, 3, 0, and 0, 0, 0, 0. So from here, we can tell that x1 and x2s are basic variables, and x3 is the free variable. So from here, we can tell that, well, the solution set is x1 equals to negative 2x3, and x2 equals to negative 3x3, and x3 is a free variable. And this tells us that there is a non-trivial solution for the given system of homogeneous equation. So therefore, we have v1 and v2 and v3s are linearly dependent. So we can find various kind of linear dependence relation among v1, v2, v3. So for example, if you choose x3 equals to 1, then we get x2 is negative 3, x1 is negative 2. That gives you negative 2v1 minus 3v2 plus v3 equals to 0. So here, note that there are infinitely many dependence relationships depending on the choice of your free variable. So we could actually form A by using the vectors given, like v1 and v2 and v3. So if you cook up columns of A using the given vectors, then v1, v2, v3, the columns of A's are linearly independent if and only if the homogeneous equation has only one trivial solution. Okay, so if the given set of vectors consists of only one or two vectors, then the situation is much more easier, and we can And we can determine the linear independence by inspection or without doing any calculation. If the given set containing a single vector, v, how can you know the given vector is linearly independent? Or on the other hand, when does the given set can be linearly dependent? Or when does the given equation has a non-trivial solution? Well, this can have a non-trivial solution only if your vector v1 is actually equal to 0. Otherwise, we won't get any non-trivial solutions because you can cancel out the component of v that forces x1 equals to 0. So, from this observation, we can conclude that the single vector v is linearly independent if and only if the vector is not equal to 0 vector. Similarly, if you have a set containing two different vectors, and suppose that the given vector equation have non-trivial solution, or in other words, the given vectors are linearly dependent, then we can move x2 v2 to the right hand side. And that gives you x1 v1 equals to negative x2 v2. And because the equation have a non-trivial solution, either x1 or x2 is not equal to 0. So let's assume that x1 is not equal to 0. Then we can divide by x1 for the both sides, which gives you v1 equals to negative x2 over x1 v2. So two vectors are linearly dependent only if one vector is a non-zero multiple of v2. So from this observation, we can conclude that v1 and v2 are linearly independent if and only if v1 is not a multiple of v2. So, using the fact above, let's pause the video and try to determine whether the given set of vectors are linearly independent or not. Okay, so did you figure these problems out? So let's solve these problems together. So for the first one, well, we can see that v2 is just 3 times v1, which means v2 is a multiple of v1. So v1 and v2s are not linearly independent. However, on part B, we can see that neither vectors are multiple of the other vector, which tells us that, well, v1 and v2s are linearly independent. So here's a theorem that states that the given set of vectors is linearly dependent if and only if there is at least one v sub I is a linear combination of other vectors. So here, the theorem is about linearly dependent and linear combination of vectors. So the theorem develops a relationship between linear independence and linear combination and span. So there's a typo in the following exercise. So if you have an old version of the lecture note, you want to correct this as if and only if, and the condition is not linearly independent, but is linearly dependent. So let's pause the video and describe the span of given two vectors using geometry. Okay, so let's solve this problem together. So first of all, to determine whether the span of UV is a line or a plane, let's quickly check whether U and V's are linearly independent. And because we have only two vectors, we can just check whether one is the multiple of the other. And because either one is not a multiple of the other, we can tell that, well, U and V's are linearly independent. So if you draw the picture on x1, x2, and x3 coordinate, then U corresponds to this vector, like 3, 2, 0, and V corresponds to this vector. So they span a plane in R2. And this plane is x1 and x2 plane. So from here, we can observe that, well, two linearly independent vectors span a plane in Rn, and that is two-dimensional object of the given space. And we can generalize this to n-dimensional or n number of vectors. So n linearly independent vectors in Rm span n-dimensional subspace of the given space. Okay, so let's prove the statement of the part B. And this is our first proof of this course. So let's prove this direction first. So this arrow means that we're going to assume the left part of the statement. So we're going to assume that W is the element of span of U and V. And we're going to prove that the given set are linearly dependent. So let us suppose that you took W from span of U and V. Then we can tell that W is the linear combination of U and V. In other words, if you move W to the right hand side, then this gives you C1U plus C2V minus W equals to 0. And the vector equation here has non-trivial solution. Like x1 is c1, x2 is c2, and x3 is -1. And this is equivalent to say the given vector, the given set of vectors, u, v, and w's are linearly dependent. Conversely, so now we're going to assume that the given set of vectors, u, v, and w's are linearly dependent. Then theorem 5 above gives you that at least one of the vectors is a linear combination of other vectors. So suppose that W is that one vector, which is the linear combination of the other two vectors. In other words, if W is the element of span of U and V, then we are done. Because this was what we wanted to prove. And we need to take care of other cases. So suppose that, well, if U or V's are linear combination of other two, then we can say, like for example, if U is a linear combination of V and W, then we can say U equals to C1V plus C2W for some C1 and C2. Then we can solve for W by moving V to the left-hand side and divide by C2, which gives you W equals to U minus C1 times V divided by C2. And this gives you W is a linear combination of U and V. And at the same time, we get W is an element of the span of U and V. And you might want to ask a question like, what happens if C2 equals to 0? And that's actually a good point. So if C2 becomes 0, then from here, we get U equals to C1 times V. But note that we proved in part A that this is not possible because U and V's are linearly independent. So we've shown that if W is an element of span of U and V, then it is equivalent to have the given set of vectors like U, V, and W is linearly dependent. So using this fact, we can visualize the relationship between span and the linear dependence. So if U, V, and W's are linearly dependent, then W is an element in span of U and V. In other words, W should belong to the plane spanned by U and V. On the other hand, if U and V and W's are linearly independent, then this tells you that W is not on the plane spanned by U and V, but the vector W should point somewhere outside of the given plane. Sometimes linear dependence is automatic. So suppose that you have more vectors than the number of entries in each vectors, then the given set is linearly dependent. So what this means is that if you have more columns than the number of rows, then the set of column vectors should be linearly dependent. So for example, if you look at the exercise below, so suppose that you have u and v and w in that way, then the augmented matrix of the given vector equation is given by 2, 3, 5, -1, 3, 6, and 0 and 0. If you RREF the given matrix, then the best case scenario should be you get 1 here, 0, 0, and some numbers here. And there's no room to cover the variable x3 over here, which gives you x3 as a free variable and also gives you non-trivial solution. So in this case, so if you have more columns than row, then this will always give you a free variable, which means we can find a non-trivial solution that implies the set of vectors is linearly dependent. Okay, so lastly, if the set contains 0 vector, then this is linearly dependent. And this is because if, say, v sub I equals to 0, then we can tell that, well, 0 times v1 plus 0 times v2 plus and so on plus 1 times v sub I plus 0 times v sub I plus 1 plus 0 times v sub I plus 1 plus so on till 0 times v sub p, and this is certainly equal to 0, which means the vector equation has a non-trivial solution, which is 0, 0, and 1, and 0, and 0.